Imagine a defense system that has protected humanity for billions of years, an invisible force field that wraps around our world, keeping the worst of the universe outside. This shield doesn't stop missiles, and it certainly doesn't stop gravity, but without it, our lives, our civilization, and the very air we breathe would vanish in a cosmic blink. We are talking about Earth's magnetic field. This is arguably the most important physical structure on our planet, yet most people never think about it. Ask yourself this: what would happen if this quiet defender suddenly shut down, or if it twisted itself inside out? The constant threat coming toward Earth is fierce. Our sun spits out a stream of charged particles known as the solar wind, traveling at incredible speed. Beyond that, the distant universe sends bursts of energy we call cosmic rays. These are high-energy particles that move at speeds close to that of light, and they pose a significant threat to life and technology. If these particles hit Earth unprotected, the results would be catastrophic. Our magnetic field works tirelessly, quietly deflecting these massive threats. But how can an invisible field stop energetic particles? The source of this protection lies deep inside our planet. The Earth's outer core is a vast sea of churning, liquid iron and nickel. The movement of this hot, electrically conductive material generates powerful electric currents. These currents create the enormous magnetic field that projects out into space, forming a giant magnetic bubble around Earth. This process is often called the dynamo effect. The strength of this resulting field is far greater than we usually appreciate because it is designed to extend tens of thousands of kilometers into space, well beyond our atmosphere, to confront the incoming solar wind long before it reaches us. This giant magnetic bubble is called the magnetosphere, and it is our primary defense against the hostile reality of space. Without it, the space environment is far more violent than we generally understand. Think about that. If we lived in space on the International Space Station, we would require careful radiation mitigation and radiation shielding to remain safe, especially for longer missions. On Earth, we rely on this natural, passive shield to do that job for us automatically, 24 hours a day. The field isn't static though. It's always moving, twisting, and changing. Our magnetic North Pole, the geographic North Pole, is where the axis runs through, but the magnetic North Pole is where a compass points, is currently speeding up, moving quickly towards Siberia. This movement is a minor detail compared to the main concern, the instability of the field itself. SMET, the field's strength is determined by the chaotic motion of the liquid iron core, which sometimes leads to dramatic instability. It weakens, stabilizes, and sometimes completely reorganizes itself through a magnetic pole flip. A pole flip is exactly what it sounds like, a process where the magnetic north and south poles trade places. This is a normal planetary process that has happened many times throughout Earth's long history. But the real threat isn't the flip itself, it's the weakened state of the magnetic field during the transition. During a flip, the magnetic field doesn't just instantly reverse, it gradually loses strength, potentially dropping to as low as 10% of its normal level. Over this long period, the orderly dipole field structure, the familiar north to south magnet shape, collapses into a messy, unstable mess. The protective bubble becomes patchy, riddled with holes and weak points. Instead of one strong shield, you have dozens of smaller, weaker magnetic pockets all over the planet. How often does this pole flip happen? The geological record tells us that these full reversals happen, but they are infrequent on human timescales. However, periods of extreme field weakening or brief, failed reversal attempts are much more common. Throughout Earth's history, full magnetic reversals have happened about once every few 100,000 years. The last complete flip happened roughly 780,000 years ago, which means we are currently overdue based on the long-term average, though there is no way to predict exactly when the next full reversal will begin. The duration of this chaotic flip phase, where the shield is weakest, is what causes the biggest concern. These transitions are not fast. The period of instability can last for thousands of years. Imagine living on Earth during a thousands-year period where your primary defense system is crippled. The resulting issues would range from technological chaos to profound long-term biological change. The effects of a weakened field are already evident in space technology. Even in low Earth orbit, where the International Space Station resides, astronauts must account for cosmic ray exposure because radiation risk is present even within the Earth's natural protective layer. If the overall global field weakens significantly, it's not just satellites that suffer. Terrestrial infrastructure faces severe threats too. The primary and most immediate threat from a weakened magnetic field involves space weather hitting Earth's surface. Events that usually generate beautiful aurora light displays, but which would become weapons directed at civilization. Solar storms and coronal mass ejections, or CMES, are huge eruptions of plasma and magnetic fields spat out by the Sun. Our magnetic shield normally deflects the majority of this material, but in a period of weak field strength, this plasma would penetrate deep into the atmosphere, causing profound electromagnetic interference. Think about global communication. Satellites orbiting Earth are the vulnerable first line of attack. These machines, which handle everything from banking and internet traffic to weather forecasting and military communications, rely on stable electromagnetic conditions. Increased bombardment by charged particles and cosmic rays would lead to immediate, widespread failure of delicate electronics, even those rated for space. We would lose global positioning systems and worldwide communication would be severely disrupted. The digital foundation of modern life would collapse in a cascade of technological failure. However, the threat gets much closer to home. The most damaging effect would be on our power infrastructure. When solar plasma hits Earth's magnetic field, it creates geomagnetic storms. If the magnetic field is weak, these storms penetrate the atmosphere and induce huge electric currents within the longest conductors on Earth: high-voltage power transmission lines and pipelines. These induced currents, known as geomagnetically induced currents or GICS, are not the familiar AC electricity that runs your home. They are powerful, low-frequency currents that flow through the grid, placing impossible stress on critical components like step-up and step-down transformers. A few major solar storms in the past, when the magnetic field was normal, have already shown us the danger. The 1859 Carrington event, the largest recorded geomagnetic storm, caused widespread telegraph system failure, sparking fires and delivering electric shocks to operators. If an event of that scale happened today during a magnetic pole flip where the shield is weak, the resulting GICs would overload and permanently damage thousands of high-voltage transformers across continents. These transformers are complex, expensive, and require months or even years to manufacture and install. Losing the magnetic shield completely, even temporarily during a prolonged flip phase, would be an extinction-level event for global infrastructure, resulting in a worldwide blackout that would last far beyond a few days. Civilization relies completely on the flow of electricity, and removing that fundamental underpinning would cause societal collapse. If the magnetic field disappeared permanently, the most existential threat to all life is not radiation or electricity failure, but the stripping away of Earth's atmosphere. The air we breathe would slowly, silently leak into space. The solar wind, composed of charged particles, is constantly pushing on the outer layers of our atmosphere. Normally, the magnetosphere creates a buffer, diverting the solar wind so it flows harmlessly around our planet. This is similar to how the solar wind flows around the entire solar system, creating the heliosphere which shields us from interstellar gas and cosmic rays. But without the magnetic shield, nothing deflects the stream of energized particles. The solar wind would continuously bombard our upper atmosphere, delivering kinetic energy that allows atmospheric gases, oxygen, nitrogen, and water vapor to gain escape velocity and be blown away into space. This is atmospheric stripping. It's a slow burn, not an instant explosion, but it is irreversible. Over millions of years, Earth would lose its thick, life-sustaining blanket of air. As the atmosphere thins, the consequences would worsen. First, temperatures on the surface would fluctuate wildly. The atmosphere acts like a climate control system, distributing heat around the globe. Losing it means areas facing the sun would overheat, while the night side would plunge into extreme cold. Second, the protection against micrometeoroids and space debris, which normally burn up harmlessly in the upper atmosphere, would vanish. The surface of Earth would become increasingly pitted and dangerous, similar to the Moon or Mars. Third and most dire is the breakdown of Earth's other crucial shield, the ozone layer. The ozone layer, which protects terrestrial life from the sun's most damaging ultraviolet radiation, is naturally maintained by the interaction of solar radiation and atmospheric oxygen. High-energy particles penetrating the atmosphere interfere with the chemical processes that create and replenish ozone. If the solar wind is constantly stripping away our atmospheric gas and disrupting the formation of ozone, the ozone layer collapses. This collapse leads to a flood of unfiltered ultraviolet radiation reaching the ground. The world without a magnetic shield and a thinning ozone layer would be a place of surface catastrophe. Exposure to massive amounts of unfiltered solar ultraviolet radiation would initiate a planetary-scale environmental crisis, threatening every living organism on Earth. For humans and animals, this would mean immediate, severe increases in cancer rates and cellular damage. The constant high level of radiation would quickly affect DNA and biological processes. More devastatingly, the impact on the global ecosystem would be nearly absolute. The greatest damage would be done at the foundation of the food chain, marine phytoplankton and plants. These organisms are highly susceptible to ultraviolet radiation damage. Widespread extinction of phytoplankton, the tiny drifting organisms that produce a significant portion of the Earth's oxygen and form the base of marine life, would lead to a collapse of ocean ecosystems. Terrestrial plants, unable to cope with the increased radiation, would also die off quickly, leading to global crop failure and starvation. The combination of atmospheric loss, ozone collapse, and biological devastation would make the planet uninhabitable for large, complex life forms like humans within decades, even if the atmosphere wasn't stripped away immediately. Could humans survive this? Humanity's only hope for survival in a magnetic fieldless Earth would be rapid, massive construction of underground or deep-sea habitats. We would need to build structures thick enough to provide radiation shielding. Just as astronauts planning missions to Mars prioritize radiation mitigation, we would need to replicate those extreme safety measures on our home planet. Cities would need to move beneath the surface, shielded by tons of rock and soil. Agriculture would rely exclusively on shielded, enclosed hydroponic systems. Surface life, as we know it, would cease to exist. The Earth would become a high-radiation, climate-chaotic desert, occasionally visible under eerie, permanent auroras, which are no longer beautiful light shows but indicators of existential doom. However, this is not a hypothetical scenario for every planet in our solar system. For one world, this failure is already a fact. That world is Mars. Mars serves as a stark, dramatic demonstration of what happens when a planet loses its invisible shield. We know Mars was once a warm, wet world with a dense atmosphere capable of supporting liquid water on its surface. Today it is cold, dry, and has an atmosphere less than 1% as dense as Earth's. This transformation occurred because Mars lost its global magnetic field. Unlike Earth, which maintains a churning liquid core that drives its dynamo, Mars's core cooled down and solidified billions of years ago. When the planetary dynamo stopped, the magnetic field collapsed, leaving the planet naked to the forces of the solar wind. The result was inevitable: atmospheric stripping. The solar wind continuously bombarded Mars's upper atmosphere, eroding it particle by particle over time. The once thick Martian sky was blown away into space, leaving the planet defenseless. Any surface water evaporated instantly, and Mars became the cold, radiation-blasted world we observe today. Now, if we turn our attention to future missions, Mars provides important lessons for human space travel and survival. The lack of a global magnetic field is why radiation safety is a top objective for planned missions to Mars. When astronauts do finally land on Mars, they will face a continuous hazard from galactic cosmic rays and sudden, intense solar particle events. For these astronauts to survive long-term and establish a base, the creation of effective radiation shielding and infrastructure is paramount. Autonomous Starship vehicles are planned to fly uncrewed precursor missions to Mars specifically to pre-position supplies and test high-risk technologies, including methods for radiation mitigation before humans arrive. The harsh Martian environment, lacking the magnetosphere that protects Earth, forces mission planners to adopt solutions that prioritize radiation protection. This includes testing local Mars materials for their shielding capabilities and deploying monitoring stations to collect continuous radiation data. The survival of future space missions, especially long-duration trips to Mars and beyond, depends on overcoming the same radiation threat that would destroy Earth without its magnetic field. Astronauts and spacecraft operating outside Earth's substantial magnetic protection must contend with two major sources of radiation: galactic cosmic rays and solar energetic particles. Galactic cosmic rays penetrate deep space and are difficult to shield against. Solar energetic particle events, often associated with solar flares and coronal mass ejections, can be sudden and incredibly intense, giving crews only minutes to find shelter in specialized radiation-safe zones. For crews aboard the International Space Station, the risk is managed partially by the station's location within low Earth orbit, which still receives some protection from Earth's field. However, the move to deep space requires engineered solutions. Future programs, such as NASA's Artemis program aimed at returning humans to the Moon and preparing for Mars, dedicate substantial research to radiation health and protection. The challenge is complex. How do you shield a spacecraft without adding massive, expensive amounts of material? This is why uncrewed missions play such a major part in preparation for human arrival on Mars. Early starships are designed to deploy infrastructure elements and test long-duration performance of radiation shielding systems. They must validate radiation models with on-site surface measurements, ensuring that the protocols developed on Earth are effective in the actual Martian environment. Think about the importance of these test missions. If the automated systems fail to protect equipment or measure radiation incorrectly, the mission planners learn what needs to change without risking human lives. This iterative testing process is fundamental to ensuring the eventual human crews are safe. We cannot afford to miscalculate radiation risk on a multi-year mission to Mars. Ultimately, surviving deep space means replicating, artificially, the protection Earth provides naturally. Whether through thick materials, specialized water tanks acting as shields, or even magnetic shielding technology, overcoming the lack of a global planetary field is the defining safety parameter for human expansion into the solar system. Let's return to the ultimate terrifying question. What would a fully fieldless Earth look like to the human eye, both immediately and over the long term? Immediately, the most visible change would be in the sky. Auroras caused by charged particles entering the atmosphere would no longer be confined to the polar regions where the field lines naturally converge. They would be visible globally, possibly stretching from horizon to horizon, a continuous swirling display of color that signals constant, dangerous exposure to cosmic threats. All electronic devices relying on GPS would fail, communication satellites would die, and the global power grid would experience simultaneous, irrecoverable collapse due to geomagnetically induced currents. The immediate world would go dark, silent, and chaotic. Over days and weeks, the invisible damage would accelerate. With the ozone layer breaking down under constant solar bombardment, ultraviolet light would sterilize the surface, targeting crops, forests, and the oceanic phytoplankton that provides the majority of Earth's oxygen. Ask yourself this: what do you do when the base of your food chain begins to crumble? In the long term, Earth would resemble a high-pressure, slightly denser Mars. Solar wind erosion would continuously strip atmospheric particles away, resulting in a planet exposed to the full, raw energy of the Sun and the galaxy. The beautiful blue marble we see from low Earth orbit would eventually turn into a pale, dry husk. Its essential gases bled into the void. The magnetic shield is not just a scientific curiosity, it is a fundamental ingredient for habitability. It determines whether a planet can retain an atmosphere and sustain complex life. The story of Earth's field is the story of our survival. If Earth's magnetic field were to vanish, the fate of our species would depend entirely on our ability to quickly build enclosed, radiation-safe habitats deep underground, replicating the kind of extreme shielding that Mars mission planners anticipate. It would be a fight for existence, mirroring the dangers astronauts face when they leave our planetary magnetosphere behind. We rely on planetary physics, billions of kilometers below our feet, to shield us from billions of light-years of hostile space. This silent, chaotic dynamo deep within the Earth's core maintains the magnetic bubble that makes life possible. We know that this shield weakens, and we know that it reverses, causing periods of extreme vulnerability that threaten our sophisticated technological world. We also know by observing Mars the catastrophic fate awaiting any world that loses this fundamental protection. The constant work on radiation mitigation and shielding for future deep space missions planned using vessels like Starship serves as a direct, expensive reminder of the protection we currently take for granted. Every moment spent developing autonomous infrastructure on Mars that addresses radiation risk confirms the danger of cosmic rays that our magnetic field handles without effort. Understanding what happens if we lose this shield is a sobering exercise in planetary science. It forces us to confront the fragility of life and the narrow margin of safety provided by our place in the cosmos. It reminds us that existence is a function of chaotic, powerful forces, controlled only by physics we barely comprehend. The magnetic field is proof that sometimes the most important structures in the universe are the ones you cannot see. The dangers of radiation exposure outside of Earth's atmosphere, which we must solve for deep space travel, are the same dangers that would instantly arrive on your doorstep if our shield failed. To continue exploring the universe, we must understand the precise threats that exist outside of our planetary safety net. Click here to learn more about the real danger of space travel and see why astronauts dedicate hours every day to minimizing personal risk. I'll see you there.